Okay, this is a third talk, Zoom talk on our program, History and Literatures in Math Science. And this is the joint program between CMSA in Harvard and Tsinghua University, where we start the talks by Schmidt and John Cox in China and myself in China. And now we have last two talks given by Joe Harris and Simon Donaldson. Today we have Lydia Bieri, who will talk about black hole formation. And she was in Harvard about 10 years ago, and she's now a professor in Michigan, University of Michigan. She is a leader for the general relativity dynamics, and she has done tremendous important works. And I am very glad that she can give this talk today. So, Lydia.
Thank you very much. Thank you very much, Yao, and thank you all, your team at Harvard, for making this possible. So I'm going to share my screen, my slides now. Okay, so I hope that everybody can view the slides now, so they should be online. Okay. So we will talk about black hole formation today, and I'm going to do that within a mathematical setting. So the main idea of, the main focus of today's talk will be on the formation of black holes through gravitational waves, so focusing gravitational waves. And that was a main breakthrough result of 2018 by Demetrios Chrstodoulou. And we will form the talk with a framework at the beginning about Einstein equations, what's the setting of general relativity, what are the interesting questions, and also when we look at the universe, or maybe a part of the universe like a galaxy or a binary black hole system or stars, so we can formulate them, we can look at a certain moment and translate this information into a mathematical language that I will describe later. And so we can use this as initial data and then evolve this data under the Einstein equations. We'd like to know what happens in time. So for instance, if a certain initial data does not yet have a black hole, how does a black hole form later? So I'll give a certain framework at the beginning, and one of the many intriguing features of general relativity theory that was developed by Einstein, Albert Einstein and other people, but Albert Einstein's name is the main contributor. So in 1915, where he thought, yeah, we unify space, time, and matter and energy. So basically everything which is in it into a space-time manifold. So we will see the Einstein equations in a moment. The solutions of the Einstein equations is a space-time manifold, which can depict, for instance, which can be a model for our universe if we do cosmology, or just an isolated system such as a galaxy and see how it evolves, or a black hole. An interesting feature of this mathematical or general relativity, I will call GR here, is black hole formation. So this is the typical singularity, we would say, in GR. There are other forms of singularity that we will discuss later, but typically a black hole is surrounding singularity of the Einstein equations. Now, I will give an overview a little bit of the history with related questions, but of course it's a huge topic, black holes, so I will not go into all the detailed branches, but streamline some of the important ideas to understand Christodoulou's work of the black hole formation when gravitational waves themselves focus. So gravitational waves, you can think of, they are produced in our universe typically when two huge objects merge. So this could be neutron stars or black holes, or during a supernova. So then you have, for instance, when black holes merge, you have a certain amount of the mass that is transformed into gravitational radiation. And this radiation itself is the changing of the space-time. These are these ripples in the space-time in our universe. And we will see more of that. So we'll discuss Demetrios Chrstodoulou's result and of this black hole formation through gravitational wave focusing. And they're interesting, it's an interesting method, and there are new ideas in there which are actually really opening up doors to other areas in PDE, mainly in hyperbolic PDE. So people have applied these ideas already in various ways. So there are interesting applications beyond GR also for the future. So that's the idea, the plan for today. And I also ask you if you have questions, so please, could you maybe send them at the end of the talk? I will be happy to answer questions at the end of the talk. All right, so here first, our black hole. Well, what we see here is a zoom in. We don't see the black hole here, but that's a zoom in into our own Milky Way galaxy center. And at the center of our Milky Way, there's a huge black hole called Sagittarius A star, which it sits there in the center, and from which, when we look at the dynamics of the surrounding stars, we can measure and compute its mass. So that's basically our black hole, if you like. Here is the famous picture that was released by the Event Horizon Telescope collaboration last year. So this is the Messier 87 object. It's an elliptical galaxy, which also at the center has a black hole. All right. So black holes are, for the moment, we can think of them as these are very densely concentrated objects where the curvature of your spacetime is so strong that it really bends the space-time around it so much that it sucks in a lot of the material which is close by, and it really deflects light. And we see that also in gravitational lensing out in the universe. Now, Albert Einstein in 1915 formulated his general theory of relativity, and here are the Einstein equations. Let me just explain. On the left-hand side, we have the Ricci curvature tensor, r mu nu minus 1/2 g mu nu, which is the metric tensor, times r, which is the scalar curvature. So you can think of this as the geometric side in the first approach. And on the right-hand side, we have, here I put the constant to 8 pi, T mu nu, which is the stress energy tensor. Now, if you have a fluid or electromagnetic waves, or we want to model a neutron star, for instance, so we put the corresponding matter or energy fields on the right-hand side into the stress energy tensor, and we provide the extra equations. For instance, if you have an electromagnetic field, we have the electromagnetic, so we have the Maxwell equations, and the system would be the Einstein-Maxwell system of equations. Now, we are interested in this talk in 4-dimensional space-time. So the solutions of these equations are, we're looking for the metric. So this gives us a 4-dimensional manifold where G is a Lorentzian metric, which solves the Einstein equation. So that's the idea. Now, if the right-hand side is 0, then the Einstein equations reduce to the Einstein vacuum equations. So we can show then that that 4-dimensional space-time Ricci curvature is 0. So it might be a bit intriguing. Vacuum doesn't mean it's really empty. It means still there's energy there. The black hole solutions I'm going to present in a moment that Schwarzschild and Kerr found are actually solutions of these Einstein vacuum equations. Also, the main result by Christodoulou of 2008 is a solution of these Einstein vacuum equations, where he shows if you have enough gravitational wave energy coming in from infinity, enough energy in a well-defined way, then a black hole will form. And this is within the regime of the Einstein vacuum equations. All right, so for the first approach, we understand the black hole region as a region of the space-time that cannot be seen from infinity. I will explain that a little bit more closely as we go on, but a typical singularity of the Einstein equations really bends the space-time, as we see here in this picture, in an extreme way at the up to infinity in some sense at the center of this singularity. But the interesting thing is, you can think of if somebody, let's say, is sitting inside the black hole, if this were possible, and trying to send out light. This is not possible because light is bent back. And if we are far away from a black hole, we cannot actually see any information from the black hole when we think of ourselves at being at infinity, which means far away at this point. Okay, so here are, I will present more about the details later, but the first black hole solutions, or the first solution for the Einstein equations generally was given by Karl Schwarzschild on the left here on the picture. And he found a static black hole solution, so a spherically symmetric solution of the Einstein equations. And Roy Kerr on the other picture, so he found a solution of a rotating black hole. So more will come about that later. So let me say maybe a few words about the Cauchy or initial value problem for the Einstein equations. When we look at the Einstein equations, then it's probably not clear at the beginning how should we formulate an initial value problem, and where do we see that it's actually a hyperbolic system of equations. So this took quite a while in the 1920s and 30s for people to understand, and many people worked on that. But the culmination of the Cauchy problem was really Yvon Choquebriat's work on the well-posedness of the equations. I'll say that in a moment. Let me first say that we will look at two types of initial value setup here. One I mentioned already in a sense that, so let's look at the galaxy, for instance, which we think, well, this galaxy generates curvature, but the next one is so far away, we think of these as being asymptotically flat. So when we are far away, we can assume that the space-time that is modeling this galaxy is going to flat Minkowski space at a certain rate. So in order to model that, we can take basically a picture at some time t0 and look at the space region. So the space-like hypersurface of the space-time would then be this picture at t equals 0, which is a space-like Riemannian hypersurface. And so when we evolve in time, then the Einstein equations will tell us what will happen to this initial data. And so Yvon Choquebriat here in this picture will just discuss her well-posedness result in a moment, but the classic approach is given here on this slide, which I just basically said in words. So I also need to mention the Einstein equations, they decouple into a set of evolution equations for the initial data and in a set of constraint equations. So we cannot just provide or prescribe any type of initial data. This initial data has to fulfill already a portion of the Einstein equations, which is called the constraint equations. And then we can think about evolution, evolving the data along a time function. So already in the 1920s and 30s here, for instance, Darbois noticed that there actually exists some constraints in GR when he looked at the initial Cauchy, the Cauchy problem of an initial space-like hypersurface and found, yeah, I can write the metric in these coordinates, for instance. So I can write the metric like here on this slide. So I have n, this is a function which we call the lapse function in front of my dt squared. Then I have plus, we have the ni in front of the mixed dx dt term, which is a shift vector, plus the spatial part of the metric here. So Lichnerowitz looked at these cases also, but in the analytic situation and in various different other assumptions, but it took them really until 1952 that Yvon Choquebriat in the general setting showed, well, we have a well-posedness theorem for the Einstein equations that she proved then. So this is one type of initial data that I just mentioned. So you have a three-dimensional manifold with a Riemannian metric. Then we prescribe a symmetric 2 tensor that is going to be the second fundamental form then. And this initial data has to fulfill this constraint equations, which is a portion of the Einstein equations. Now, a Cauchy development, I will call in the future of this data, is now a globally hyperbolic space-time, which is a solution of the Einstein equation. So that part that we can write as an evolution equation that we can then also basically transform into hyperbolic equations. Now, and an embedding, so my initial data embeds into my space-time in the obvious way so that we get the first and second fundamental forms here. So that's the classic type of initial data problem. And I mentioned briefly asymptotically flat in heuristic terms. So again, when we look at isolated systems like a galaxy or a black hole or two black holes, then we think of this as being concentrated in a compact region, but outside of this region, the complement is then diffeomorphic to a complement of a closed ball in R3. So the metric and the second fundamental form decay to 0 in certain ways. So I don't specify how fast here, that's, we'll see things later. Okay, that's asymptotically flat. That's the setting we're interested in. Now, the well-posedness result by Choquebriat of 1952, she gave it for the Einstein vacuum equations, but it has been generalized by her and other people to many other matter and energy fields. So let me read the first theorem here. So we give initial data, I call it H, G bar K, so that's in the initial Riemannian space-like manifold, which satisfies the vacuum constraint equations. Then there exists a space-time, which is a solution of the Einstein vacuum equations, and we have an embedding of H into M, being a space-like surface with induced metric G bar and second fundamental form K. So that's the well-Posedness result. It was a big breakthrough, and what we do today, if we want to understand the dynamics of the gravitational field, so we are building our results on this result, or maybe a generalized or generalization of it. So then later with Bob Garage in '69, so they showed the following problem, theorem. So let's take an initial data again of this type, satisfying the vacuum constraint equations. Then they showed there exists now a unique globally hyperbolic maximal spacetime, which is a solution of the Einstein equations, and again the embedding H into M is now a Cauchy surface with induced metric G bar and second fundamental form K. So a Cauchy surface we think of, so if you have a time-like or a light-like curve, so then it intersects this surface exactly once, not 0 times, not twice. So this is what we also understand from global hyperbolicity. All right. Okay, so then here, just in the middle, I have here a picture of Noether. So Noether theorems you certainly are familiar with from other types of math and physics. So in other words, here in GR, we have to think a little bit about what should be the right energies to work with within the PDE theory. So a large portion of the proof of also Christodoulou theorem, I will have to discuss about energies, etc. So one main challenge is if you want to do, let's say, show that the solution exists and maybe is either does not have singularities or does from black holes, etc. So we need to find energies that we can use in a comparison argument to control the curvature of the manifold. And the spirit of Noether theorems will be all over the place in the proof that we'll study today. Now, the second way we can set up an initial value problem, we call the characteristic approach. That's the one that is more, let's say, designed to actually address questions from gravitational waves. So remember from before, we had basically a picture from a portion of our universe at the time t0, let it evolve in time, and here we do something else. Now, let's think of, you can think for the moment of special relativity and then have this generalized into general relativity. But when I'm sending out light, so in GR, light is the speed of light is the fastest we can go. So, and we ourselves, everything else moves slower than that. So if I send out light or electromagnetic waves, so they travel along light cones. This is like you have, as an interesting picture, we can have the wave equation in mind, excuse me, where we have a domain of influence and domain of dependence. And similarly here we can think of the light cone as well. This is the boundary of where I can influence my future. If I'm sitting here, so the light cone towards my future and its interior is all I can influence in the future. And similarly, I can go backwards. Now, when I send out gravitational waves, they go at the speed of light along this, I call it light cones, but well, in our manifold, that's a null hypersurface with a lot of structure, of course. But we can think of them as generalized light cones. Now, this is a very natural way to set up gravitational wave initial data because, as I just said, they travel along these null hypersurfaces. So instead of this space-like surface, we now look at first one cone that is going out, so an outward light cone, and then inward light cone. So on my picture here, so I have this surface S. S is going to be a space-like 2 surface in my manifold, space-time manifold. Now, at each point on the tangent space, I can actually identify 2 orthogonal directions. The outward, I call it outward and inward direction. So future-directed null vectors. In the outward direction, I can call this L. Here the index piece, I'm just at the point looking at the vector. And the inward pointing one, I always have an L underline, an L bar. Now I can create vector fields. Here again, the outgoing direction will always be vector fields that I have that will be called L, and in the ingoing direction, I have generating vector fields that are called L bar. So I can think of sitting on this 2 surface and then generating this null hypersurfaces in the outgoing direction and in the ingoing direction. And the corresponding light cones or null hypersurfaces outwards I will call C, and inwards will be C bar. Now, of course, if you have now gravitational waves, if you want to study gravitational waves, then a very natural thing is to set up this initial value problem as a characteristic initial value problem, namely on cones or intersection of cones. So what we have here, instead of the space-like slice, we have now two intersecting cones that intersect here in this surface S. This is a space-like surface, as we just saw. And now we can say, well, how do we set up an initial value problem for that? Actually, these are the results by Alan Rendell in 1990. So he solved the local characteristic initial value problem for the Einstein vacuum equations. And that also goes into Christodoulou's work. So there were earlier works also by Chateaubriand, Müller-Zumhagen, and Seifert on this topic. All right. Now, maybe I will talk a lot later in this talk about, first of all, the main theorems, but also how to set up this initial data. I don't want to say too much here, but I will explain how this initial data will be set up in later. But we can think of it as black holes, or actually as we send out lights, and we understand black holes, etc. So sitting on the surface where light is traveling basically is a natural setup. Now here, let me cite Rendell's theorem. So he showed in 1990 that if you have characteristic smooth initial data for the Einstein vacuum equations on a null hypersurface C1 and C2 that intersect transversally on a space-like surface, I call it S, then there exists a non-empty maximal development, again my manifold MG, of the initial data bounded in the past by a neighborhood of this surface S in C1 and C2. Now, in order to prove the closed trap surface formation, so here's a new word, I'll explain that in a moment. So black hole formation is tightly related to the formation of an interesting geometric object, namely closed trap surface. I will explain that in the next few slides, but this is a geometric object that we have to understand that this is Christodoulou's result is showing that we have a closed trap surface from formation and then eventually a black hole. So in order to do that, we consider data, so Christodoulou considered data which is trivial up to a surface S, if you think now of this intersecting null cones. And in the context of Rendell theorem here, this would correspond to our C, the outgoing null cone, to the future of S being C1, and C2 in Rendell theorem is the incoming Minkowski cone, C bar rooting in S. So he will give Minkowski data on C bar, but we'll see how this is done in a bit later. Okay, now to understand closed trap surfaces, let me explain the following. So we look at S as a hypersurface now in C or C bar. So we look at this space or at this two surface and we let it flow in the outward cone or in the inward cone. And we can define the second fundamental forms of S in the outward direction, and I will call this chi. And the second fundamental form of this surface in the inward light cone or null hypersurface, and I will call this chi bar. So outward doesn't have an underline, so chi and chi bar is outgoing, second fundamental form, ingoing. Now the traceless parts of this we call the shears, and I will denote them by this chi hat and chi hat bar. These are the shears. And if I take the traces of them, then I get the trace of chi that I will sometimes denote as theta plus, and the trace of chi bar as theta minus, and we call them the expansion scalars. Now you can think if you, they measure how these light cones of these null hypersurfaces actually expand, well, or contract in a way. So now we call S a trapped surface if both of these traces are zero. So trace of chi bar is typically zero, that's the inward going cone, but typically if we don't have a black hole, for instance, sitting there, the trace of chi would be actually positive, because you could think of sitting on the surface S and going an infinitesimal amount towards the future. Typically in an outward going light cone, the area of the surface S will increase. But now this trace chi negative tells me that actually the area will decrease. So a closed trap surface is characterized by the fact that both of these traces are negative. And that's depicted in this, this drawing I have here. So the outward going light cone is bending, so has a decreasing area element in that sense. Now, let me also define marginally out-attract surfaces, so-called MOTS. So again, we have now S, our space-like surface, and if both traces of chi and chi bar are negative, this is a trapped surface. Now let's look at just the outward null normal for the moment. So we have this theta plus, so the outward, the trace chi. If this is negative, we say this is S is out-attract. If it is equal to 0, we call this a marginally out-attract surface, a so-called MOTS. Now, a few remarks here. So in the time-symmetric case, a MOTS is simply a minimal surface. And so a MOTS, so these were important objects also in the proof by Rickshaw, Chain, and Xintu Yao in the positive mass theorem. And now interesting also is that cross-sections of the event horizon, so basically the boundary of the black hole, in the sense the boundary of the domain of the region that cannot communicate anymore with null infinity. So the cross sections of this event horizon in asymptotically flat stationary black hole spacetimes that obey the dominant energy condition are outermost MOTS. And outermost MOTS can arise really at as the boundary of the trapped region. So this has been also studied by Anderson, Metzger, Meyer, and other people. So here is just a picture to give you some idea. So these MOTS arise naturally in several situations. So for instance, if you have a stationary black hole spacetime, like in the first picture, so then basically the cross sections of the event horizon is a MOTS. Now, if you look at other types, so dynamical black hole spacetimes, then typically these MOTS occur inside the event horizon of a black hole. So these trapped surfaces are really the key ingredient to study black hole formation. Okay. Now, a few more words about the initial value problem that we are going to set up to understand the formation of black holes. So we have seen that in the classic initial value problem, the constraints for the initial data are given by elliptic PDE. Well, I didn't show you this PDE, but these are elliptic PDE. In the characteristic initial value problem, they can be actually written as ODE, and it's much easier. We can solve them along the way. So we can specify some data freely and solve propagation equations along generators of our null hypersurfaces. Now, as we said, for gravitational radiation, the characteristic treatment of this initial data problem is the most natural one to look at. Here is some just what also is produced by black holes. So black holes also are at the source of really black hole gravitational radiation a lot. So if you have two black holes, they're spiraling around each other, they will get close to finally merge to one black hole. The black hole goes on its time-like curve, but there will be gravitational waves sent out. And these gravitational waves travel along these null hypersurfaces out to future null infinity, here depicted as I+. I call this, I'll give you the definition in a moment, but this is future null infinity. We can think of ourselves when we do observations in astronomy or with LIGO, that we are sitting there and looking backwards these null hypersurfaces to get information that were sent out by, for instance, a black hole merger that we receive here and can understand. All right, just a little summary here. So we are talking today about the non-cosmological settings of isolated gravitating systems like black holes. We have seen some local well-Posedness result, the famous result by Chrstodoulou, the maximal extension theorem by Her and Garage. So sometimes we are interested to show that there are no black holes, that we have a solution which is complete for all time. Sometimes we would like to produce black holes. That's the main topic of the talk. So we will here use the foliation of the spacetime by a time function, and also what I call here optical functions, U and U bar, will show up later. I will define that later. Okay, just for the moment, if you do not want to produce a black hole, then you would appreciate this theorem. So Christodoulou and Kleinerman on the opposite side show me there's no singularity, proved that if you have asymptotically flat data of a specified kind, and you have smallness assumptions again in a well-defined sense, then this asymptotic flat data, which is globally close to the trivial data, to Minkowski, will give a solution to the full Einstein vacuum equations for all time. This will give you a complete spacetime tending to Minkowski again at infinity along any geodesic. So here, this is, for instance, you look at some data and you ask, will a black hole form later or not? So this is on the other side, saying no. Under these assumptions, if you have small data, in some sense, no, you don't. So this has been generalized in various ways here. I'm not going into details, but I want to show you if you do not want to form black holes, then this is this kind of result that you're interested in. And one more word here about gravitational waves. Here we see a picture where two black holes spiral in. They will finally merge and send out gravitational waves. And again, these gravitational waves give us a lot of information about the source. These are these fluctuations of the curvature of the spacetime. The spacetime itself is changing, it has ripples. And the big breakthrough really was also happened in September 2015 when the LIGO team for the first time ever measured gravitational waves from a binary black hole merger. So that's really the beginning of a new era. And so LIGO, Virgo, and now also the Kagura, the Japanese detector, have been taking data, and they have seen many, many events. So that's really signs of the future also. Now let me go back to the black hole solutions. And before I go to talk about Christodoulou's result itself, let me remind you of some of the highlights in black hole science. And again, I apologize to some people. I cannot be really saying everything. Here's a huge topic. I will streamline the most important ideas that will come up in the proof. It will be helpful to understand the proof today. So the first solution to Einstein equations per se was Karl Schwarzschild's solution in 1916. Namely, he found a solution which is spherically symmetric and depends on the mass. I call it M here. It describes the field outside of a non-rotating star or black hole. So it could be star as well. So generally outside of any spherically symmetric object. Now the hypersurface R, that would be the radius, equals 2m is an event horizon. That was understood later only, but that's the so-called event horizon, which is, we can think of this as the boundary of the region, which is causally connected to infinity. And causally, I mean, I can interact either with a light-like or time-like curve. So it will be important for the domain of dependent theorem later. Now, Roy Kerr in 1963 discovered the so-called Kerr solutions. So this is now a two-parameter family of axisymmetric solutions, which also has an event horizon. And this spacetime is outside of this horizon is a regular asymptotically flat region. So we don't only have the mass, but we have now also the angular momentum. So angular momentum A, which is characterized about this axis of symmetry. All right, there's other solutions with charge, etc. I do not want to go deeper into that. We could fill a whole semester with this beautiful theory. And now you can perturb these exact solutions and see what happens. So that's the Kerr stability problem, for instance, a huge, interesting topic that hopefully will be solved in the near future by our colleagues. So what we want to do is we want to investigate stability and dynamical properties of these fields. And here I will always use the null infinity. So what is future null infinity? Again, we're sitting within an asymptotically flat spacetime. We want to solve the Einstein equations, the vacuum equations for asymptotically flat initial data. Now, future null infinity, I call it I plus here, is defined to be the endpoints of all future directed null geodesics along which R goes to infinity. And it has a topology of R cross S2 with the function U taking values in R. So we have a function U that will be retarded time at null infinity. So this null hypersurface is CU, so they intersect I plus at infinity in a two-sphere. I will denote by S infinity U because for time or R going to infinity. So with that, actually, the black hole region can be defined. So this is the clean geometric definition goes back really to, I would say, Roger Penrose set up the notion of null infinity in a clear geometric way. So this allows us to define the black hole region geometrically now. So we define the black hole region of an asymptotically flat space-time to be the set of points B within that space-time which are not in the past or future null infinity. So here I have a little note. So the past I denote of a point I denote by j minus of p, and the future would be j plus of p. So this is actually the set of all points in the manifold Q in M, for which there exists a past-directed causal curve initiating at P and ending at Q. So when we write for the black hole region, so that this would be the complement in the manifold. So we have M here without this past of future null infinity. So in other words, everything inside the black hole cannot communicate with us when we are sitting at future null infinity. That's where we are doing observations. All right, so that's the geometric definition of what a black hole region is. Okay, so I'm going to go through a few highlights regarding black holes and black hole formation. And again, so I feature the results which are most important for what we're going to discuss later. So already in 1939, Oppenheimer and Snyder studied gravitational collapse for a pressure-free fluid ball of uniform density. So the space-time geometry outside of the ball in the vacuum region is then given by the Schwarzschild metric. So they looked at this gravitational collapse. In 1983, there's an interesting result by Xingtu Yao and Richard Schoen. They proved the existence of a black hole due to the condensation of matter. So in particular, what they showed is that the energy density, so minus the magnitude of the momentum density of matter on a space-like hypersurface, is now everywhere bounded from below by a positive constant in a region which is large enough in a suitable sense. So then the space-like hypersurface must contain a closed-trapped surface which is diffeomorphic to the sphere S2. So that's really an interesting result. Okay, so that's, you see here we have the black hole formation or existence of a black hole due to condensation of matter. So later on, we'll talk about gravitational waves. All right, so I also mentioned a few other results along the way. I don't want to spend too much time on these because we're going to focus on something else. But in a series of papers in the 80s and 90s, Demetrios Chrstodoulou already investigated gravitational collapse for a spherically symmetric scalar field model. So, and there's a lot of interesting results, and one of the main interesting things he found that he can show black hole formation in this setting. So of course, for certain assumptions on the data, etc., he gets black hole formation out. He also showed that for certain classes of initial data, something really intriguing happens. So they do not form a black hole, but they actually form naked singularities. So these naked singularities, we can think of their singularities in the space-time, which are not hidden within a black hole. So there's no horizon around them. So they could be seen from far away, from null infinity. And in another paper, he showed, well, within the classes of data that he studied, they are unstable. There is still a big open question if you look at more general models. Well, could they really occur more often? Is it really unstable in the general case? So these are really interesting open problems for the future. All right, so then in 2003 and 2005, Michaelis da Fermo studied a model where, in addition to the scalar field, he also had an electromagnetic field. In particular, he showed that part of the boundary of the maximal development of this Cauchy horizon is a Cauchy horizon, through which he could, the metric itself can be continued only in a C0 matter, but at which, in generic cases, the Christodoulou symbols are not square integrable. So basically, the mass blows up. So there were more studies by da Fermos, Rodnyansky-Luke, and other people along those lines. And I want to mention maybe one of the most recent results by da Fermos, Michaelis da Fermos, and Jonathan Luke. So they started work studying the interior of dynamical rotating vacuum black holes without symmetry. So in 2017, they proved that for well-specified Cauchy data, the maximal Cauchy evolution now can be extended across a non-trivial piece of the Cauchy horizon as a Lorentzian manifold with continuous metric. So, and here, let me also mention Christodoulou's results on, well, he looked at, he introduced a new model in GR, and he introduced this new model, which is called the two-phase model, where you look at hard and soft phases of a fluid. And this model was designed to capture some of the features of stellar gravitational collapse. Now, I'll say more about applications later, but just before this result, there's also a lot of interesting related results to black hole formation you can find in shock formation, for instance, in fluids, in a perfect fluid form. So, for instance, Christodoulou also investigated shock formation for the perfect fluid of an arbitrary state, so Euler equations in 3 dimensions, and he studied in the special relativity framework. So we can think of similar problems in other fields, and certainly shock formation in fluids is one of these. I'll say a few things more about applications later on. So now let's go to black hole formation through gravitational waves. And here I'd like to cite the story that Dimitri likes to tell. So when he was a grad student with John Wheeler, so John Wheeler told him in 1968 that, well, you should study, he said to Dimitri, the formation of black holes in pure general relativity by the focusing of incoming gravitational waves. And Dimitri likes to make jokes in the sense that, yeah, well, if Wheeler hadn't changed his thesis problems, then he would have just graduated in 2008. So, of course, his thesis problem was then an excellent other problem that he studied, but this was the motivation. And in 2008, so Dimitri really accomplished in a monograph of 600 pages, the full resolution of black hole formation through the focusing of gravitational waves. So let me now go to this in general. Now, one of the most important theorems we should first cite before we go and understand more about Christodoulou's work on black hole formation. Let's look at Roger Penrose's famous result about, it's sometimes called the singularity theorem. I think it's more correct to call it the incompleteness theorem. So again, we think of a black hole as a region which cannot be observed from infinity, and we have seen that the close trapped surfaces are tightly interwoven with the existence of a black hole. Now, Penrose proved that a space-time, let's call it mg, is future null geodesically incomplete if the following 3 conditions hold. Now, the Ricci curvature has to be positive, greater or equal than 0 for all null vectors v. There exists a non-compact Cauchy hypersurface H in M, and there is a close-trapped surface S in M. So you see, this data has already needs to have the surface S already present, and then he can say, well, then the space-time is incomplete. So a version of this theorem that we will use later in the proof is the characteristic version, if you like. So now consider regular characteristic initial data on a complete null geodesic cone. And we denote again mg our maximal future development of the data of C. And we assume now that M contains a closed-trapped surface, then our space-time mg is future null geodesically incomplete. So this is the incompleteness theorem by Penrose that will play a crucial role now in what's going to follow. Okay, I will give you the most precise version of Christodoulou theorem later, but for the moment, let me give you a first version. So the first version of Christodoulou's black hole formation result is simply, well, not simply, it's quite intriguing, but it sounds very nice in a simple version. So we see the closed-trapped surfaces form in the Cauchy development of initial data, which are arbitrarily dispersed if the incoming energy per unit solid angle in each direction in a suitably small time interval is large enough. So the word to look at here, the energy is large enough. So we should keep this in mind. So we will introduce some more of the setup for this problem and give you a more precise version of the theorem later along the way. But this is the main theorem that Christodoulou proved. Here's Christodoulou in his office. So that's Demetrios Chrstodoulou, and now we want to understand a bit more of the black hole formation. So if you think of the black hole formation result by the focusing of gravitational waves done by Christodoulou in 2008, so we have basically we find that there are 2 main theorems. So one is the existence theorem. So first we have to prove that the space-time exists long enough and is sufficiently nice. I mean by that sufficiently smooth, so no focal points, for instance, such that a closed-trapped surface can form. The second theorem is the closed-trap surface formation theorem. Namely, we have to prove indeed the formation of a closed-trap surface in this setting. So it's interesting to see that second theorem is going to be much simpler. The first theorem is really where all the labor goes into. So to show that the space-time for a long enough time, if you like, is behaving nicely is really the main efforts of the whole proof. So that's a really subtle theorem to establish, and that will take up most of the discussion in the following. So we will now sketch the ideas and the proofs of this theorem, and along the way develop the data that Christodoulou used to prove the theorem. So these are two pictures that will show up again later, but at the moment, so we would like to consider a space-time MG, solutions of the Einstein vacuum equation, so a manifold with boundary, which is a smooth solution of the Einstein vacuum equations, I mean, up to as many certain derivatives, so such that the pass boundary of M, and in this picture, the pass boundary of M is the future null geodesic cone. So C0 is the future null geodesic cone, and here in the other picture, so I have just this depicted it here. So we have the future null geodesic cone C0, which is starting at the point I call O here. So, and I will give initial data on this outgoing cone C0, assuming that it is trivial in a neighborhood of O itself, and that our manifold, the space-time manifold, is to be a development of this data. So we will see that I will. So maybe let me jump to the next slide. I will come back to this slide in a moment. I will just want to have you read also the first part. So we now look at the unit future dielectric vector field, the time-like vector field T, at this vertex O. And I have a geodesic generated by T such that the tangent vector at O is to each null geodesic generator has a projection T along T. So let me just go back and see, yes, we're having our time vector field here. Gamma 0 is my geodesic generated here by T, and the outgoing null cone, the initial future null cone from point O, is my C0. So moreover, we now look at generators of C0. They are parameter, so this outgoing initial null cone hypersurface. So this is parameterized by an affine parameter S, which is measured from our vertex O. And such that this S is the parameter of the geodesic null vector field, I call this L prime along C0, which is tangent field to each generator. I'll have more pictures in what follows, but now again, along C0, we have the generating vector fields that we call now, this is the vector field L bar for the moment. So then the initial data is now given on C0, but also Christodoulou assumes that it is trivial for S less or equals than some R0. So let's say we have some value R0, which is bigger than 1. Then for the parameter values less or equals than R0, we give trivial data. So what this means is that they coincide with the data which is corresponded to a truncated cone in Minkowski spacetime. All right. And from that, we see that the boundary of this region with trivial data is a round sphere of radius R0. In particular, each generator extends up to parameter value R0 plus delta, where delta is going to be a constant, which is between, well, bigger than 0 and less or equals than 1. All right, so this initial cone is assumed to have no conjugate or cut points. And let me go back here again. So we have this initial cone, and let's say we have here a sphere of radius R0, where from the vertex up to this R0 value, we have trivial data. And also along this incoming null cone, we have, so we don't give data there, but we have trivial data here, and we're going to give initial data where R0 is bigger, where S is bigger than R0 here. And so this is going to be the region D prime in this picture. Now let me say a little bit more about the remaining structures. So the domain of dependence theorem, of course, guarantees us now that the solution spacetime itself will have a region which is Minkowskian. So I give trivial data on some parts of this cone, so the generated spacetime will have a Minkowski region. that is given exactly by the path of a backwards light cone that I will call C bar E of a point E. I will go back in a moment on this geodesic gamma 0 at the distance 2r0 from the vertex O. So what I just said here, you can still see. So here is my point E. I have here, this is the initial sphere or diffeomorphic to a sphere surface S with R0. And we have trivial data here up to this point. And now if I go towards the future here, then I see, oh, well, I have a backwards light cone starting at this point E. And all this here in my backwards light cone is going to be Minkowski region by the domain of dependent theorem. And so we introduced the advanced time function U bar on C0. This is just going to be defined by, we have here our parameter S minus this R0. That's going to be what we call advanced time, and I will call it U bar. So in the proof later, the spacetime will be constructed from initial data, whereby the level sets now, the CU bars of this U bar function, are going to be incoming null hypersurfaces. So you can think of this now, this is the outgoing null hypersurface C0. We have other outgoing null hypersurfaces we can construct, but now we have incoming null hypersurfaces CU bar. And basically the non-trivial region that we have to show that there are no focal points or cut points, that this exists long enough that eventually a closed struct surface can form is this region here, which in the future I can truncate here with a space-like slice max hypersurface I call H-1. All right. So just to recall, there's a lot of notation I'm introducing here. So we have initial data, which is given on a complete future null geodesic cone C0, with data being trivial for the parameter values S less or equals to R0. So we consider the restriction of the initial data to S less or equals to R0 plus delta. So which means the U bar, the advanced time, has values between 0 and delta, where the data is trivial for U bar less or equals than 0. And again, in the picture, again, U bar, maybe here you can see it now, so U bar equals 0 is along this incoming null hypersurface, and then U bar is increasing up to this delta. This is the other boundary in terms of U bar, or this U bar equals delta. Okay. Now, what we also have at the vertex, we have seen, we have, we set U equal to U0 equals minus R0 at the vertex itself. And as we see, 2U minus U0 along gamma 0 equals exactly then the arc length from the vertex itself. So U is determined everywhere in this sense. So therefore, we will have a space-time that we want to construct. It will be bounded in the future by this space-like hypersurface H-1, where U bar plus U equals -1, and by this C bar delta. So we call this development, the development M-1, and we call the non-trivial region of the development M-1 prime. Here the pictures are again. So here this is future bounded here by this H-1, and then we have this region here. And so we are, here you see maybe a little bit better. So this region is the non-trivial region that we are interested in. All right. So here is a second formulation of the existence theorem. So now I will construct initial data in what follows in more details, but let initial data be given in this setup, and we choose delta to be sufficiently small. Then the maximal development under the Einstein vacuum equation contains a region M-1, where a specific foliation can be constructed such that the null hypersurfaces CU and C bar U bar contain no cut or conjugate points. So this manifold, this space-time region M-1 is bounded in the future by the space-like hypersurface H-1 and the incoming null hypersurface C bar delta. So that's the existence result, and the proof of that will be the main object in the remaining part of the talk. Now this is the existence result, but we also have the closed struct surface formation result. So the second theorem, as I mentioned at the beginning, can be now formulated as follows. So Christodoulou showed he takes K and L to be positive constants such that K is bigger than 1, bigger than L. let initial data be given as we described above roughly. I will give them later in a more precise version. And we assume that now this R0 squared divided by 8 pi, the integral times the integral from 0 to delta of with respect to du bar of a quantity E that is defined just below here. E is 1/2 chi hat squared basically. So G with this slash here, this is actually the metric, the induced metric on the sections S within C0. So this object, this 1/2 chi hat squared, is an invariant of the conformal intrinsic geometry of C0 itself. So we integrate over this object. So this has to be greater or equal than k over 8 pi. So here with the integral along C0, where u bar is taken from this interval from 0 to delta for some delta. So now then, if delta is suitably small, the maximal development of this data contains a closed-struct surface S, diffeomorphic to S2, and has area which is greater or equals than 4 pi L squared. So you see we have this something which has to be large, so we can think of this this left-hand side here, the integral over this object E, and in a small enough, let's say, advanced time interval where delta has to be small enough. So we can think of this as really as concentrating gravitational waves come in and concentrate concentrate within a small delta there. Okay, so let me explain a little bit more structures. I have a few more minutes to do that. And we will give an idea of the proof and go through the ideas of the proof. Again, we have a double null foliation by functions u bar and u. We have the incoming and outgoing null hypersurfaces, and the intersections I will call C, S, u bar, u. So these are space-like 2 surfaces. Also, we define the space-like surfaces ht by u plus u bar being equals to time t. So, of course, you can expect the Einstein equation to have a lot of interesting dynamics, so this foliation should not exist for very long because things will happen. And so, but it will exist up to a null hypersurface C bar delta and a hypersurface HC for small delta, and let's say we have U0 strictly less than C, strictly less than 0. All right, so here's another picture. So again, we have some data here. We have the outgoing null hypersurface, and here this incoming null hypersurface is C bar, U bar. We have to look at now. All right, maybe I just get along. So we will sketch the proof, and let me introduce a little bit more structures. So the optical functions we call U and U bar, these are actually optical functions. They are obeying the so-called eikonal equations. So each of them obeys the eikonal equations given here on the top of these slides. Now we can introduce 3 null frames related to this structure, namely the future-directed null geodesic vector fields. I have L prime and L bar prime. Again, L is in the outgoing direction. Everything with a bar goes in the incoming direction. So I can define them L prime mu, for instance, like -2, I contract with the metric G mu nu, D nu u, and correspondingly I have the corresponding object here, but instead of u, I have u bar. So this is the in and outgoing null vector fields prime. I will sometimes use the following definition. So I can also, from this is defined a positive function, omega. Namely, I plug in G L prime, L bar, and this is equal to -2 omega to the minus 2 times omega to the -2. And omega we can think of as the inverse density of the double null foliation. So, oh, there's a prime. So we can define it this way. So the normalized vector fields we call them L hat and L prime hat. They are then defined as follows. So I have L hat is then omega times L prime. L hat bar is omega times L prime bar. And they will satisfy when we plug them into the metric LL bar hat. This is equal to -2. So I have the first set of vector fields I call L prime. And the second one is denoted by L hat. And then I have a third one I just call this pair of vector fields L and L bar, which again, I take the omega squared now of the primes, not omega, but omega squared the primes, which gives me L and L bar. So it's convenient to use these different vector fields along the way. So for us, it will be interesting to see LU is 0 is equal to L bar U bar, but if I have LU bar and L bar U, this is actually equals to 1. So this will be convenient to use them in various ways. All right, so now we look at the generators and flows. The integral curves of L are the generators of the CU, outgoing null cones, parameterized by U bar, and correspondingly we can write this down, integral curves of L bar, which are generators of the incoming null cones. Now we define a flow phi tau, which is generated by L on any outgoing null cone, and a flow phi bar tau generated by the incoming vector fields in these ways. So we can create flows, I call them phi tau and phi bar tau, where we go from, let's say, the initial space-like intersection to S U bar plus tau U, and the other one maps S to S U bar U plus tau. So this is actually very convenient if you want to introduce good coordinates. So they yield a canonical coordinate system. And it turns out that for these purposes here, the stereographic coordinates on the sphere are especially good to use. All right, so we will introduce and use these coordinates. Here again, let me remind you, we have trivial data on this part of the outgoing cone. Here we give non-trivial data, and we're interested in showing the existence of our space-time solution in this D bar region now. All right, so in these coordinates, we can write L and L bar in very nice ways. So L bar is just DDU, and L is DDU bar plus this term where I have BA times DD theta A. And BA is given by this object here in the middle. So I have dBA du, which is equal to 4 times omega squared. And this C A that I have here is the theta itself is just a torsion. And if I have the what I have here, so I just define the theta dagger A to be I contract here with the inverse metric on the sphere, or on the surfaces S, okay? And theta is the torsion one form. Now the metric in these coordinates takes simply this form here. So we can write the metric in these coordinates in this form as is given here at the bottom of the slide. All right, with that we can proceed to more general ideas. What are the main ideas of the proof? Now the main ideas and methods of this proof, we can identify 3 main methods. So the first method is a generalization of the energy method, which is well known in PDE theory. And here I remind you of Noether's idea of conserved quantities. So a summary of this means we have energies we have to construct. They control the curvature, which again controls other geometric quantities in a bootstrap argument. So that's the main idea. And so in order to construct these energies, we have to do that with respect to useful vector fields. We'll see them in a moment. So in the first method, we estimate the Weyl curvature through energies given by the Bell-Robinson tensor using appropriate vector fields. The second method is the foliation of the spacetime in a crucial way, namely by this double null foliation. And the third method is a new one. So Christodoulou and Kleinerman have used method 1 and 2, well, 2, not in the double null foliation, but they had a space-like and an outgoing null foliation in that work. And it has been used before by, for instance, Kleinerman-Niccolo to look at the outside Minkowski stability problem, or by Christodoulou also in shockwave problems. So the new thing here is really the short pulse method introduced by Christodoulou in this very proof. And method 1 is more, let's say, designed for GR, but method 2 and 3 are really have wide applications in all sorts of hyperbolic PDEs. And the short pulse method I have to discuss a little bit further. So maybe for the energies, let me just say a few words here. So we do not have really, as we can transform away the gravitational field at the point, so there's no real, let's say, natural or obvious object to call energy here. But in terms of, let's say, PDE theory, where we want to find good energies to control the solutions of PDE, so this role will be played by the Bell-Robinson tensor in general. But let me remind you first that we have the Bianchi identities for any wild tensor W. This is a traceless tensor that fulfills the Bianchi identities. And so more generally, for a wild field W on MG, which is a full covariant tensor field with the algebraic properties of the wild or conformal curvature tensor. Now the Bianchi equations for W are the following linear equations here, so in the middle. So I have the divergence of this is equal to, on the right hand side, the J beta gamma delta, which is the wild current. All right, so the wild curvature, if you work with Einstein vacuum equations, the curvature is indeed the wild curvature. So let me say now the Bell-Robinson tensor, this is the energy quantity that we work with, so it's defined here. So Q is basically a quadratic of the wild tensor given in this formula, and it satisfies an interesting or really useful positivity conditions. And if W, my wild tensor, fulfills the Bianchi equations, we also have the divergence-free property here at the bottom. Now, let me also introduce the deformation tensor. So we will introduce interesting good vector fields to control the energies or to set up energies. The deformation tensor I denote by pi hat with respect to a specific vector field y. And so this will measure, so we define the deformation tensor like that to be the trace-free part of the Lie derivative of the metric with respect to a special vector field y. All right, so interesting roles will be played by the so-called commutation vector fields. And so from our Bell-Robinson tensor, for a given wild curvature tensor here, we will define the energy momentum density vector field that we'll call P associated to W and with 3 multiplier vector fields. So let's remember the last formula here. So I have the energy momentum density vector field P. I plug off the Wald curvature where I can plug in 3 multiplier vector fields here. So we will use that to set up the energy and fluxes in the future. So let me not go into the foliation. We have seen the foliation of the CU and CU bars, but I would like to say something about the short pulse method. So let me take maybe another 5 to 10 minutes to finish that, the whole talk. So the short pulse method is really new, and it says, well, in a specific way, it treats the focusing really of incoming waves. So there's a certain hierarchy that the curvature components have to obey in order for black holes to form. And again, in some sense, we can think of large incoming energy during a small time interval. So let's see what this means. So the short pulse, so I will give you the data in a moment, but in the characteristic initial value problem, so we are prescribing some data on CU bar 0, and we have some free data, some free and some prescribed data. So we have a full set of initial data. Now the free data, what is that? So the free data is given by a 2 covariant symmetric positive definite tensor density, which is called M, on the sphere depending on U bar, and M itself is of weight -1 and the determinant 1. So in particular, we can write M as the exponential mapping of some psi, where psi is actually in S hat. What that means, so S hat is denoted the space of symmetric trace-free 2-dimensional matrices. So this is the exponential map of psi, which is a symmetric trace-free 2-dimensional matrix. So in a natural way, we have the exponential mapping from this S hat space to the unit upper hyperboloid, for instance. So these are the transformation rule turns out to be especially simple for stereographic charts on S2. So we want to understand more of this initial data. So here's the short pulse ansatz. So we consider arbitrary 2-dimensional, smooth, symmetric, and trace-free. Now these are matrix valued map, psi 0 on S2. So I have an initial map psi 0 on S2 that depends on S, the parameter between 0 and 1. And that extends smoothly to S less or equal than 0. Now this is the interesting setup of the data. So we introduce our psi, which is then depending on U bar and theta, as delta to the 1/2 divided by U0 absolute value times psi 0, where this depends on U bar divided by delta and theta. And again, the U bar is taken from the 0 delta interval, so this should be actually theta on the other hand, not delta. So this is a theta is on the S2 sphere. So what does that give us? With this type of initial data, here what I have is curvature components. So alpha, beta, etc. Here, these are curvature components. So R, so we only have the wild part of the Riemannian curvature of our Lorentzian manifold. So R is actually a wild tensor. And if I contract it with X and Y are tangent vector fields tangent to these surfaces S U bar U at some point P. And again, L hat this outgoing direction, L bar hat this incoming null direction. So if I contract alpha with L and L twice, and I have this object, so this is a specific component of my wild curvature tensor, so I can look at the supremum of the absolute value of A on this cone CU0. This is less or equals than O2 of delta to the -3/2 U0 to the -1. So I'm not going to read through all of the slide, but I would like to point out a few things. So we have these curvature components that I call alpha, beta, rho, sigma, multiplied here by the area form of CS, beta bar and alpha bar. And these are these components given by the contraction with these vector fields. And now we see this hierarchy showing up, this short pulse hierarchy. So look at how these components depend especially on delta at U0, of course, but especially on the delta. So we have a delta -3/2 here, goes to delta -1. Then we have just the U0 to the -3 for rho and sigma. And then the beta bar again is delta, but times U0 to -4, and then you have a delta 3/2. So this appearance of this delta parameter is really what we call the short pulse hierarchy. So in particular, this dependence on delta for the curvature component. So we have a nonlinear hierarchy. And you can see that in a linear case, this would look very differently. And it's really this hierarchy is really important. It's actually required for trapped surfaces to form in the space-time manifold here. So the main challenge is really to prove that also this hierarchy is preserved in the evolution. All right, let me maybe say a few words here just about the vector fields. In order to prove that this hierarchy is actually preserved in the evolution, we need to find the right vector fields with specific weights that we use to define our energy and currents. The energy and currents that I defined above. So we have multiplier vector fields that are L and K. K is defined here just as U squared times L bar. And for each wild field here, which is curvature and modified Lie derivatives of the curvature, we define an energy momentum density vector field P. And here the X vector fields are replaced by the multiplier vector fields. So the commutation vector fields are given by L, S, and O. O are just rotation fields on the surface S, and S is given as U times L bar plus U bar L. So these are the commutation vector fields. Now modified Lie derivatives on this L hat of the curvature are taken with respect to these commutation vector fields. All right, now let me just briefly tell you. The details are kind of intricate, but a rough summary of what kind of energies and fluxes we have. We can define the total, let me call it a second order energy momentum tensor. So the P, remember from before. So we have these energy momentum densities and up to a certain order. So they are defined over the wild fields in a specific way. And I will not go into all these details here, but we define these energy densities. The other objects that we need are the specific energies, which are depending on U. And these are integrals on the outgoing null cone CU. And we also define the fluxes. I call them F. They depend on the U bars. So these are integrals defined via integrals on the incoming null hypersurfaces of some 3 forms, which are dual to these energy momentum densities that I call P up here. So we need P, and we define the energies and the fluxes, the energies on CU and the fluxes on the C bars. So from these, we now look at, we take the, again, I don't want to go into details, but we take the supremum of these energy quantities in this way over U. We take the supremum of the flux quantities in this way over U bar, and we would like to work with them. All right, so in order to complete now, there's the whole idea of the proof is a continuity argument, as I said. So you have an initial data set up, and you prove a continuity argument in the following. So we want to bound the quantities in terms of initial data at the end. So in order to complete this bootstrap argument, so the final piece relies on just the divergent theorem here in space-time. Here is again our data. So I give some data on CU0 here, and I have some region V that is bounded by the incoming null hypersurface here and the outgoing here on this side. So we have the divergent theorem tells me that, well, the energy is at some function U minus the energies at the initial U0 plus the fluxes F at U bar is equal to the divergence over this space-time region V of my stress energy densities P. So the divergent theorem in its nice and simple form will come in here. So this will allow us to bound the data at some function value U by initial data. So here I basically just summarize how this all goes. I mean, when you're familiar with geometric analysis, then maybe that's not so, that's a trivial thing, but I would like to address also, let's say, people are not really familiar with this, just very briefly. So the argument of this, well, we have now the maximum of all these energies and fluxes from before to be bounded using the divergent theorem. So we denote this by the max by P. Now we use the local results by Choquet-Briard and Randall together with the large continuity argument to get some existence result. So, and the rest here just describes the continuity argument. So we have a smooth solution in this space-time slab where I take out the vertex geodesic. And so for some C, which is bigger than U0 plus delta, the solution extends now smoothly to the boundary of U bar equals delta. So the bootstrap assumptions hold on my manifold I call MC. And now P itself, this stress energy density, is bounded by F of ID is just a function depending on initial data. And this is to be defined along the way of the proof. You cannot, you have to find out what it really is. So it's bounded by a function of the initial data. So we show that our initial set of real numbers here, where C is living in, from U0 to -1 is actually not empty. Then we set C star to be the supremum of that set. And we show that the inequalities in the assumptions are not saturated at C star. So the bootstrap argument is then fulfilled when we show the strict inequality at C star. So therefore, we can extend the solution smoothly beyond C star for some epsilon, as long as epsilon is small enough. So our C star, therefore, is really here -1. So that's a very short explanation of the bootstrap argument in this setting. All right, so I have maybe 2 more minutes to finish a little bit. So the proof, so this existence result is really a bootstrap argument where I just highlighted the ideas of the proof in just before. Now the existence of the closed trap surface is much easier to prove because we have by the proof of the previous theorem, we have understood a lot of the structures of the space-time already. Now, in order to prove the closed trap surface formation, we can say, well, remember this M-1 star is the space-time slab that we had to construct. So here we have that the trace chi bar plus 2 over U is given, is less or equals than O of delta U to the -1, where delta is sufficiently small, and trace chi bar is negative everywhere. So in order to show that we have a closed trapped surface, really a trapped surface, is indeed, this is now true if and only if everywhere on the surface SU bar U, the trace chi of the outgoing null hypersurface, the trace chi is negative, strictly negative. So we also found in the previous proof, there's a lot of information when we do that comes out. So we find the structure for the chi-hat squared. Remember the energy, let's say, supplement there that we integrated over was chi-hat squared, 1/2 of that. So this is of this specific order, delta to the -1, u to the -1, well, u to the -2. So in the proof now, in order to show closed trap surface formation, these two structures together, we can derive from them in a straightforward manner that the trace of chi now has to be negative. So it's deduced really from the chi hat squared 1/2, which is the E quantity that we had before. So we can use all the structures that we have developed in the existence theorem to prove that the trace chi is actually negative. And maybe just one remark. So Christodoulou, at the end of his huge proof, constructs explicit initial data and shows that now the presence of this closed trap surface in space-time implies the existence of a black hole. He uses then Penrose's theorem again to show, yes, the black hole is there. All right, maybe just one more minute. I mean, I have to summarize a little bit. So let me explain a little bit generalizations that have been done. So Kleinerman and Rodniansky generalized this original proof by relaxing the initial assumptions. So mainly it follows the line of Christodoulou, but it introduces some new solutions to the more general situation. So they have one lower degree of differentiability and less is assumed from the beginning on the incoming radiation. So further relaxations by Kleinerman, Luke, Jonathan Luke, and Rodniansky. So they use the original existence theorem. They have derived a result. They have derived a result which is really extending in a considerable way the former result. So now they do not require a lower bound on the incoming energy in all directions. But what they have really is they consider the outer boundary of the existence domain, -1. So if you look at some neighborhood in the sphere S2 of some direction and assume that the incoming energy in the directions corresponding to this neighborhood is sufficiently large, depending on the angular size of this very neighborhood. So then the incoming C bar delta contains a trapped surface. And even though none of these sections where I look S delta U may be trapped by themselves, it is shown that there is another section of C bar delta that is trapped. This surface is represented as a graph U, let's say function G of theta over the sphere. And this surface attains a large negative values of U in the directions corresponding to the neighborhood where large incoming energy is actually concentrated. All right, so that was a vast generalization of this surface result. A really great geometric idea was given by Pongoulet, who simplified just the work of Kleinerman, Rodniansky, and Luke a lot by looking at the intersection of a hyperplane with a light cone in Minkowski space, realizing that just by these geometric ideas, a lot of this proof simplifies. There was a different proof given by Reiter and Trubowitz. There was an interesting proof also by Pin Yu, who showed for the Einstein-Maxwell equations that now not gravitational waves alone, but also by electromagnetic fields concentrating this black hole. All right. There has been work by Alan and Luke also in interesting directions. So I apologize for not citing everybody that has done work here. So I just want to cite a few of the main generalizations. So let me maybe say a few other words. So within general relativity, there has been a lot of, let's say, generalizations in all directions. And without assuming GR or going to other fields, so Shuang Miao and Pin Yu have employed the short pulse method to study shock formation in quasi-linear wave equations. So this short pulse method has a lot of interesting applications to PDEs and other fields of physics also. And so various authors have explored that in shock formation, fluid theory, and other hyperbolic PDEs. So I think there are many interesting applications of these new methods that Christodoulou came up with, especially the short pulse hierarchy. And maybe I should stop here. And just mention there's a lot of interesting questions to work on. There's more to understand when we couple Einstein equations to other matter fields, how black holes form in general situations. There's a lot of open and interesting problems to explore out there. And yeah, I thank you so much for listening.
Great, thank you very much, Lydia. So let's see whether there are questions.
Okay.
You find any questions? Right.
Okay, let's see.
Fine.
Oh, I got a few questions here in the.
Okay.
Okay, let me just see. All right, so. Okay. So there's one question who asked, does the short pulse method point to a hierarchy in the Einstein equation? So there were two questions somewhat related to that. And well, I think it is a hierarchy in some sense to, so the first answer to this question is, well, if you really want to see if gravitational waves, or how can you form a closed trap surface by the focusing of gravitational waves? So in that sense, there is a hierarchy for that specific problem in the Einstein equations, yes. To ask, for instance, well, is this hierarchy, is there more to that? So I think it always depends on the questions you're asking. And for this specific problem, so this is a specific hierarchy that we see, especially also in the nonlinearity of the Einstein equations that Christodoulou has found. So this really depends very much on the nonlinearity, and it shows for these questions, yes, this is the special hierarchy that is provided by the Einstein equations. Now you can ask probably other questions like, well, is there, in other problems, are there other types of hierarchies? And I think that is what is now being explored and has been explored by other people for instance, shock formations or other hyperbolic PDEs, that it depends on the question you ask. So there are certain hierarchies given by the problem and that can be used or revealed and used by this new method. I'm reading some more questions here. I hope I answered two of them. Okay, so somebody asked me to explain the slide before questions. Can you see it now? Is it shared again?
Yeah.
Okay, so this was about the cosmic censorship. Okay, and so we have the cosmic censorship, one moment, conjectures. So let me explain that for the moment. So Roger Penrose came up with two conjectures, one called weak, one strong cosmic censorship, formulated now in various ways. So the main idea was for him to say, can we hide the incompleteness inside a black hole always? And faraway observers would not be affected by that. So that was his motivation. And the weak conjecture says, well, for generic asymptotically flat data, the resulting vacuum spacetime has a complete future null infinity. So this would mean that naked singularities would not occur generically, and that so every solution, every singularity of the Einstein equations is hidden within a black hole. So along those lines, Christodoulou showed in his 80s and 90s papers mainly that, well, for generic data for the Einstein scalar field model, you do have black hole formation, etc. But he showed under special circumstances you have naked singularities. But then again, he perturbed those and showed that these naked singularities are actually not stable within this framework. This is a very special model, and now the remaining questions for this will be, well, look at more general models or solutions of spacetimes and try to find out, are naked singularities there more generic? So that's an open question. So the strong cosmic censorship also by Penrose. So this is a conjecture again for generic Einstein vacuum initial data. The solution spacetime is determined by initial data, which cannot be extended as a suitably regular Lorentzian manifold. So in other words, we can say, we can put this into the simple phrase, the future is uniquely determined by the present. So this is the domain of dependence theorem that we hope to be true in physics. So these are two conjectures which are related to many interesting questions in general relativity. And people have reformulated them and said, well, in certain settings, maybe we can prove or disprove. So I would just leave it open here. This is a very general formulation. And these are questions that people like to understand. Okay, then let me read another. Any idea about? Okay, there's another question that I received. Any idea about the three-body problem? Well, let me say the two-body problem is not even, well, I have to say something first. So if you look at geometric analysis, and I'm not talking about numerical relativity at the moment, in geometric analysis, it's still a challenge to set up the two-body problem for extended bodies. Let's say you have two fluid masses that you let evolve under the Einstein equations. So the general setting for that is not yet understood. So these are open questions that people are working on. However, in numerical relativity, so let's say you make certain assumptions, and in numerical relativity, there are codes, algorithms, which model two black holes spiraling in and sending out gravitational waves. So I have not talked about numerical relativity here. I'm talking about the geometric analytic results. And again, the three-body problem, the two-body problem is still not solved in geometric analytic terms, and the three-body problem, therefore, neither. But I mean, if you're interested in numerical simulations, there's a lot of numerical simulations that have been done. Again, we have to verify that some of the assumptions that go into these algorithms are actually verified. Okay, I have one more question here. Let me see. Okay, one question said, so one question said, is there a ratio of formed black holes to form naked singularities? Well, this goes really into the conjecture that I have just on the slide right now. These are still conjectures. So within the simple model that Christodoulou looked at in the 80s and 90s of the scalar field model, so there the naked singularities are very rare. So they do occur, they're very rare, typical under, let's say, the right assumptions, you can create black hole formation in gravitational collapse, but the naked singularities are, in that sense, he showed that in this sense, they're unstable. Again, so we do not know yet, we have not yet the mathematical results, we have not observed any naked singularities yet out in astrophysics. I think Avi Loeb had just an interesting article about observing naked singularities or speculating. Maybe we have seen them and we don't interpret them in the right way. So there still needs to be a lot, let's say, of mathematical research done to understand if naked singularities are really that not generic, or if certain situations in full GR actually allow them more often to happen. So these are open questions. So I think these are all the questions I have seen on my end.
I think
we also have some with a hand raised. There's some with a hand raised in the audience.
Let me see. I cannot see them, sorry. Could you unmute?
I unmuted them for you.
Oh, okay, so I'm listening, yeah.
It's Jim Eisenberg.
Oh, Jim, do you have a question? Hi. Oh, here is one hand, I see. Yeah. Hi, Jim, can you hear me? Okay, so there were questions. I cannot hear anything. Yeah.
Yeah, Jim? What happens?
It looks like he's either not listening or he's having trouble with his computer.
All right, well, let's end this lecture now.
Okay.
It's getting late anyway.
Right.
So, well, it's a beautiful lecture. Thank you very much, Lydia. So we shall put your lecture in our web. And
No, I fucked it up. I did.
Yeah. Hello, Jim?
Go on.
Hi, Jim, are you there?
Yeah, I had two questions. One was, is there a 4+1 generalization of the short pulse method? A 4+1 generalization.
Right. So what was the question, if there is one?
A 4+1 generalization instead of 3+1 for black hole formation in 4+1 dimensions.
Jim, why don't we stop here, really, because it's getting very late. Many people are leaving.
Yeah, I think I couldn't hear the question.
You can communicate with Lydia directly by Zoom individually. It's getting a little bit late.
Yeah,
So let's thank Lydia for the beautiful lecture. And there will be a lecture at 3 p.m. today on quantum groups. Tomorrow, there's another colleague of Lydia who will be talking about, Bob Greiner is going to talk about finite simple groups, and we'll be we're expecting very beautiful lectures by them. And we think this lecture is beautiful and inspiring. So let's clap our hands.
Thank you very much.
Thank you.
Thank you, Yao and Ryan and everybody. Thank you all.
Okay, bye. See you later.